Hi guys, I'm SAIKIRAN from 4th year ECE. In this video, we are going to discuss about DCT from DFT and demonstration of DCT energy compaction property. We all are familiar with DFT, which gives us a frequency representation of discrete time datasets. But there are few drawbacks with this discrete time Fourier transform. They are DFT has complex valued coefficients and it also has poor energy compaction property. So DCT solves these problems. DCT is much better transform than DFT in the energy compaction because in DCT representation of signal it tends to have more of its energy concentrated in a small number of coefficients when compared to other transforms like DFT. So DCT is frequently used in lossy data compression applications such as JPEG image format. Also, due to its high degree of spectral compaction, it is a better choice in signal compression. There are mainly four types of DCT. They are DCT1, DCT2, DCT3 and DCT4. Each of these four versions of DCT is based on extending an endpoint sequence into a periodic sequence which has certain symmetry property. So coming to DCT1, it is given by the following equation. DCT1 is an exactly equivalent to a DFT of 2 into n minus 1 real numbers with the even symmetry. Coming to the DCT2, it is represented by this equation. DCT2 is probably the most used form and is commonly represented as the DCT. It is the main topic of our discussion. Coming to the DCT3, it is the inverse of the DCT2, also oftenly called as inverse DCT. Coming to the DCT4, it is represented by this equation. As I mentioned earlier, these four types of DCTs are based on the periodic extension of an endpoint sequence. So in this pic, you can observe that the difference between how they are extended: DCT1, DCT2, DCT3 and DCT4. So this is a generalized DCT formula. When we observe DCT2 and the generalized formula, there is a difference in this Km. It is called the normalization factor. This Km is equal to under root 1 by n for k equal to 0 and under root 2 by n for k not is equal to 0. It is multiplied to make the DCT2 matrix orthogonal. Now coming to the part where we compute the DCT from DFT, there are certain steps we have to be followed. Suppose there is a signal x of n of length L. For computing the DCT, first create a signal y of n which is of length 2n. This y of n is based on x of n. It is nothing but the extension of x of n. Y of n is equal to x of n when n is between 0 to n minus 1. If n is greater than n minus 1, then y of n is equal to x of 2n minus n minus 1, which means if x of n is equals to 1 2 3 4, y of n would be 1 2 3 4 4 3 2 1. After half, it will be reversed. In step 2, we compute the 2 endpoint DFT of y of n. It is calculated by y of k is equals to summation n is equals to 0 to 2n minus 1 y of n into e power minus j 2 pi by 2n into kn. Then next in step 3, we multiply the computed DFT y of k with the shifting coefficient, that is e power minus j by k by 2n. So in final step, we multiply the result obtained in step 3 with the scaling factor Km. It is Km is equal to under root 1 by n for k equal to 0 and Km is equal to under root 2 by n for k not is equal to 0. So after this, we will get the required DCT. Now let us see the mathematical derivation of DCT from DFT. In step 1, we have calculated the y of n using x of n. In step 2, we will be calculating the 2 endpoint DFT of y of n. It can be calculated by the formula summation n is equal to 0 to 2n minus 1 y of n into e power minus j 2 pi by 2n into kn. And it, as it is from n is equal to 0 to 2n minus 1, we can split it into n is equal to 0 to n minus 1 and n is equals to n to 2n minus 1. From 0 to n minus 1, we know that y of n is equals to x of n. So we can replace it. Now from n is equals to n to 2n minus 1, y of n is equals to x of 2n minus n minus 1. So we will be replacing it with, now 2n minus 1 minus n can be replaced by a variable m. Now if you replace it with m, this n can be written as 2n minus 1 minus n. Now we will be having this equation. Now we can split this equation into three parts. Now after splitting the second part, we will be having this equation. If you observe this equation, this 2n will be get cancelled, and e power minus j 2 pi into k is always equal to 1. Also we can change this m to n. If you observe this equation, we can take the e power minus j pi by 2n into k as common. So after taking common, we will be having this equation. So in this equation, both summation n equal to 0 to n minus 1 into x of n, summation n is equal to 0 to n minus 1 x of n, these both are common. And observe, if you observe these terms, these are in the form e power minus j theta plus e power plus j theta. So these can be considered as 2 cos theta. So writing this whole equation as e power j pi by 2n into k, which we have taken common, and into summation n is equal to 0 to n minus 1 2 times of x of n into cos of k times n plus 1 by 2 into pi by n. So after calculating the 2n point dft of y of n, now we will be having the equation of y of k. Now if we compare these y of k equation with the original dct equation, that is xc of k, we can observe that both have the x of n terms and cos terms. So now we can write y of k in terms of xc of k. Now in xc of k we don't have the exponential term, so we will multiply xc of with the exponential term. Also in y of k we have an additional multiple of, so we have multiplied with the 2. In xc of k we have an extra km, so we will divide by 2 to get the y of k. From it we also get xc of k with the help of y of k, that is x of k is equals to km by 2 into exponential of minus j pi by 2n into k into y of k. So it is the reason why in step 3 and 4 we multiply the calculated 2n point dft with the factors km and e power minus j pi by 2n into k by 2. Now let us look into the MATLAB demonstration of DCT from DFT. First we have considered a x of n signal 1 2 3 4. As in step 1 we have to make a signal y of n with the help of x of n, which is of the double the length of x of n. So now y of n will be 1 2 3 4 4 3 2 1. In next step we have to calculate the DFT of 2n point DFT of y of n. So we calculated the DFT of y. Now we will be multiplying this calculated DFT with the scaling and shifting properties. It is done in this for loop. This calculated value is stored in the variable DCT from DFT. Now if we the results DCT of x, it is using inbuilt function, so the answer will be 5 minus 2.230 and minus 0.15. so DCT from DFT, it is a variable in which we stored our values calculated from the DFT. If you observe these variables, these both are same. So now we calculated the required DCT with the help of DFT. Now let us discuss about one of the important properties of DCT, that is the energy compaction property of DCT. Energy compaction is the ability to pack the energy of a signal into as few transform domain coefficients. Suppose if the input signal has mostly low frequency components, then higher order coefficients of xc of k for large k, DCT tends to decrease faster than corresponding coefficients of DFT. Also, in DCT representation of signal, it tends to have more of its energy concentrated in a small number of coefficients when compared to other transforms like DFT. Suppose consider a sequence x of n shown as below. If you calculate the DFT of x of n, it is basically equal to the discrete Fourier series of the periodic extension of x of n. In this, we can observe that the discontinuities arises. Due to these continuities in the periodic extension, some unwanted high frequencies appear in the DFT of x of n, although these frequencies are not present. So, to overcome this problem, consider y of n such that y of n is equal to x of n when n is between 0 to n minus 1, and it is equals to x of 2n minus n minus 1 when n is greater than n. So it is the representation of the y of n. Now if we consider the periodic extension of y of n, we can observe that the discontinuous between edges are now eliminated. There is no discontinuities here. So this is what we do in the DCT. The periodic extension of y of n is computed instead of x of n. So the artificial discontinuities are not introduced in case of DCT. Now we will try to demonstrate the energy compaction property of DCT with the help of an example. Now consider signal x of n is equals to a power n into cos omega n plus 5, where n is equals to 0 to n minus 1. So now consider these parameters, where a is equal to 0.9, omega equal to 0.15, and 5 is equals to 0, and n is equals to 32. This is a plot of our input signal x of n, in which x-axis represents the n and y-axis represents the amplitude. So now we will calculate the DFT of the x of n, and we will be plotting that DFT of x of n into real part and imaginary part. So this is the real part of the DFT of x of n, and this is the imaginary part of the DFT of x of n. We can observe that there is symmetry. After calculating the dCt2 of x of n and plotting it here, this is the plot of dCt2 of x of n. Here we can observe that the most of the energy of dCt is contained in the lower index term than the case of DFT, where the DFT, the most of the energy is not concentrated in the lower index term. Now we will try to truncate both DFT and DCT by removing m of the frequency terms from x of k and xc of k. X of k is for DFT and xc of k for DCT. Now we will try to remove few frequency terms. Then using the corresponding synthesis equation, we will try to reconstruct the x of n. Then after reconstructing the x of n, we will try to calculate the errors between the reconstructed x of n with the original x of n. On comparing these errors, we can know that the energy compaction of DCT is greater. For calculating x of n from the DFT, we will be using the DFT synthesis equation. This is the equation after removing m of the higher frequency terms from x of k. Here m represents the number of terms we are removing. So suppose m is equals to 1, then x of n by 2 is removed. Suppose m is equals to 3, middle 3 terms are removed. They are x of n by 2 minus 1, x of n by 2, and x of n by 2 plus 1. So this xm of DFT of n is given as 1 by m summation k is equal to 0 to n minus 1 Tm of k into x of k into e power minus j 2 by kn by n, where Tm is given here. For calculating x of n from DCT, we will be using the DCT synthesis equation. So it is given by 1 by n k summation k equal to 0 to n minus 1 minus m beta of k into xc of k into cos term, where n ranges from 0 to n minus 1. Here beta of k is equals to 1 by 2 for k equal to 0 and 1 for k between 1 to n minus 1. So here we will be considering for m is equals to 1 to 31, that is we will be performing the calculations for m is equals to 1 to 31. First we will be removing one term, then we will be removing 3 terms, then we will be removing 5 terms, so on. then we will be plotting the errors. This is the mean square error functions we are going to use. This is for DFT and this is for DCT. Here x of n represents our original signal and xm DFT of n is the x of n reconstructed using DFT synthesis equation, and xm DCT of n represents the equation of x of n reconstructed using the synthesis equation of DCT. This it is the mean square error. Now we will be plotting these errors of DFT and DCT and we will be comparing them. Now these errors are plotted from m is equals to 1 to 30. It means from removing 1 terms to removing 31 terms. So we can observe that the plot, this red one represents the DCT and the blue one represents the DFT, and the x-axis represents the number of coefficients set to 0 and y-axis represents the mean square error. We can observe that the truncation error of the DCT is almost 0 up to nearly more than 20 terms, whereas compared to DFT it is greater than DCT. So with the help of these graph we can say that the energy compaction of DCT is greater because the error is very much less. So it is the reason why it is used in the data compression application such as speech and picture processing. It is more effective because the energy compaction properties are greater than DFT.